Okay, so I think people are still joining, but let me get started in the interest of time. I want to welcome everyone to this last Data Science Coast to Coast seminar of this year. My name is Jing Liu. I'm the Managing Director of Michigan Institute for Data Science at the University of Michigan. Together with my colleagues, shown here, you can see on the slides, who are the executive directors of other data science institutes, we have organized this seminar series in the hope of using it as a concrete way to foster a broad-reaching data science community that can collaborate routinely to advance our missions for research, training, and data science for social good. So in the first half of 2021, we hosted 5 seminars, taking advantage, I guess, of the Zoom environment that we are also used to right now. So today's is the last in the series. Each seminar features 1 faculty member and 1 postdoctoral fellow from 2 universities, and they are grouped by themes. The speakers talk about ongoing projects and motivating issues, and we hope this format will lead to follow-on research discussion, which will, in the long run, foster new collaborations. Today's theme is ocean dynamics. There will be 2 speakers today. Our first speaker today is Miguel Jimenez-Urias, who's a postdoctoral fellow of Earth and Planetary Sciences at Johns Hopkins University. His research focuses on the study of the geophysical fluid dynamics as the foundation for understanding basic processes in physical oceanography, focusing on processes that happen in a scale of a few kilometers to 100 kilometers, combining simulations, analytical models, and high-resolution global circulation models. He received his PhD in physical oceanography from the University of Washington. Our second speaker today is Laure Zanna from New York University. I will actually introduce her after Miguel's talk. So now I would like to have Miguel share his screen. Audience members, you can put your questions in Q&A. Depending on time, we might save all the questions till the end of both talks. So now I'm gonna stop sharing my screen, and Miguel, you should go ahead and share yours.
Thank you. See if I get this right now. Is that my presentation or?
Yes, it looks very good. Go ahead.
Well, yeah, thank you for the introduction. Actually, the title's a little different. There was a little bit of a update on the title a couple of weeks ago. The original title was sent about several months ago. Yeah, so my title is Scale-Dependent Shear Dispersion, Steering of Mixing of Passive Tracers in the Ocean. This is kind of like a funny project because it was funded by IDS, the Institute of Data Intensive Engineering Science, as a data-intensive modeling project. But somewhere early along the way, we kind of got stuck in mathematical solutions. So a full disclaimer, there is no data. It's a little bit of awkward here, but it's all exact mathematical solutions, which is kind of exciting. And the exciting part is that it can be expanded upon, which is very promising. So I'm going to talk about this kind of like, first of all, kind of talk a little bit about oceanic tracers. I mean, the emphasis is passive tracers. And the big distinction is that passive tracers do not have a feedback into the momentum of, say, the Newton's laws of what rules how the water moves in the ocean. So passive tracers are more like chlorophyll, nutrients, oxygen content. They can vary, they can be affected by the fluid, by the ocean currents. So right now in your figure, you're seeing, should have some animation here, but you're seeing temperature of the ocean. I think the objective of this animation, which maybe it's not working very well, is to show this latitude bands distribution of temperature. Even though temperature is not exactly a passive tracer, tracers are very useful because they can actually indicate how the currents move in the ocean. So the ocean, so first of all, you see a lot of differential heating in the ocean. So the equator is really filled with hot water, and the poles is really cold water. So you have a pressure gradient, and then you have a balance between that and the rotation of the Earth, essentially making everything, the fluid motion to form. There's a tendency from jets, or essentially zonal flows that go from east to west in the northern hemisphere. So that's why you see these latitude bands temperature. The Southern Ocean is kind of special because it's uninterrupted by continents. Meanwhile, where you have continents, you have strong boundary currents that have a tendency to form jets as well. So essentially, the big takeoff is just by looking at this tracer, even though it's not the passive one that I'm trying to show animation. Oh, sorry about that. It's not playing. I apologize about that. It's that you have a tendency to form jets or zonal jets in the atmosphere. They have like wide scales, but in the ocean, they're like smaller scales because the density contrast is much, much different. And modeling of ocean tracers, the passive tracers, remains an active area of research because they can indicate biological activity. They can indicate ventilation zones and mixing of oceanic water masses, how all oceanic water masses are, depending where they sink and how they mix along the way. So it's a really useful tool to study, and again, it's a very active research area. When it comes to modeling, global climate models are limited by spatial resolution or temporal resolution, mostly because they have to run very long time integrations forward in time, hundreds of years. And there's a problem with numerical instability. You have to kind of respect that. So you have to restrict, first of all, you have computer power limitations. So you have to run them that will actually finish to run. It won't take years, but also you have computer storage of data. So it's a big problem trying to resolve all of the scales. So there's a compromise between the scales that you can and you want. And usually you neglect a lot of stuff that happen at the subgrids, essentially stuff that lives within between the margins of resolution. So for example, you're seeing here the two pictures of kind of what the impact of resolution have on land. You see the top figure, it's from both of them from IPCC reports. So you have a higher resolution, but those are not, most model simulations, climate simulations, global climate simulations do not have that enough of resolution. So you have grid squares of horizontal dimensions about 90 kilometers. So anything below that is not resolved by the model. You're seeing even higher resolution, and those are really done only for regional climate simulations. So you don't have a full integration of all of the scales. So you need to include parameterizations of physics or mathematics that determine how things mix in the ocean or how things will have an effect from within a grid box out of the grid box. So that's kind of like where I am. One of the things I'm interested in is why use idealized mathematical models, and what it really is to answer simple questions and that can give you some insight into the physics and mathematics. In this case, it's really one of the stuff that I'm interested in, the interplay between different scales, between the advection, which is the transport, reversible transport, and diffusion, which is the irreversible mixing. The equation of motion is actually well known, and we're really interested in figuring out, given initial distribution, how the tracer will evolve. And what you're seeing here is actually an observation of surface ocean chlorophyll somewhere in northern on the Baltic Seas. And the really striking features that the more you zoom in, the more and more features you see that are not super smooth, but then all those features of the circulation also are features, fine scale features, so surface chlorophyll. Those kind of, what you're seeing, the smaller grid, the smaller pictures about 1 kilometer resolution. So that stuff is beyond what models can actually resolve. And going back to the mathematics, really the simple equation is essentially for a tracer, there's no, again, feedback with momentum, with energy constraints. So everything is, all of what determines the physics of the solutions or the mathematics of this is contained with a single parameter, which is the Peclet number, which measures the relative kind of what dominates either reversible motions or transport of passive tracers or the diffusive, which is irreversible. So there's a competition between that, and the Peclet number kind of like gives you that. A large Peclet number means advection or reversible transport dominates, Meanwhile, a small Pecla number essentially means that diffusion dominates. And going that along with those idealizing models is that the process of shear dispersion, which was brought up early in the 50s and then kind of been revisited and revisited and revisited. Essentially, this idea that if you have initial concentration and you have no fluid motion, it will take a long time to mix, and it actually will start mixing only at the edges, and you can actually estimate how long it will take. It could potentially take, depending on the properties of the water, it could take months to actually diffuse. This is the coffee stirrer experiment. But if you have a shear flow, that essentially means that a velocity field that varies spatially, you can accelerate that process by essentially deforming the surface and increasing the surface area where diffusive mixing can happen, essentially increasing the gradients, because that's where diffusion can be accelerated. And that enhanced diffusion is essentially is due because of the advective transport. And that's essentially the phenomenon of shear dispersion, this interaction between velocity gradients and weak diffusivities. Going back to the 80s, one of the seminal papers about this by Peter Rines, who I actually have a good fortune to get to know him and learn from him a lot. And Bill Young, his student back then, they kind of like divided into two different time scales, what they call the rapid stage, which you can see these little diagrams that will kind of be the rapid stage when you have a lot of deformation of the tracer. And then that takes time, within time scales that are really close to time equals 0. So essentially, it will take, given initial condition, the rapid stage will be the dominant one initially. And then once it deforms enough, then diffusion will take over. And that's a slow stage. Essentially, you mix, but rather than having the molecular diffusivity, you have an enhanced diffusivity, which is inversely proportional to the background, the kinematic diffusivity. So that's kind of very important because it was one of the seminal papers. One of the things about this, though, is that this kind of like theory was developed for flows that the shear is constant. So you can imagine a linear dependence on the flow velocity. So everywhere the shear, the gradient of the velocity is constant. So you have this kind of like uniform enhanced diffusivity. Something more complex could be, for example, and there's some insight about this, these are the cosine jets, or like jets that have a Fourier series expression in one component. So you can think of a cosine jet will be kind of like the simplest case scenario where you have regions in which the velocity goes to 0, has a maximum, the shear is maximum, the shear is 0 in particular places. And it's the simplest, but also the most complicated one because it incorporates a lot of really interesting dynamics there. The generalization will be the case when you have a jet in which the velocity has a Fourier expression, a sum of modes, this being the simplest case. And Peter Rines and Bill Young actually did look into this, which was very interesting. They arrived to the effective diffusivity, but then the more recent papers by Kamasa in 2010, they realized that there's two different regimes, one of them of anomalous diffusion, which characterizes long-lived tracer that doesn't decay that fast, and it gets advected. And then there's another time scale in which Taylor diffusion or the effective diffusive effect, which takes place way later. And there's a scale selection there. They did this kind of like a local analysis, essentially meaning that it's just they just look at particular regions of the flow. Another one that was actually more influential to our work was by Alimani and Park. It's actually about to be published, I think. And this is how this project started, because they derived this numerical algorithm called the macroscopic focusing method to essentially run the repeated direct numerical simulations, and from that recover the eddy diffusivities. And they tested actually against the cosine jet, and they got some good agreement. So you can see sort of a direct numerical simulation which resolves all of the scales and their method, and then they got some really interesting approximate solutions that merge. They have a very good agreement with those, and they derive some, based from that method, some inspired operators, which is very groundbreaking on their own. So this is kind of like what I took. So I started from here, and that's the solution that Alimani showed. They kind of like used an approximate method to solve it. It didn't solve the initial condition, but it essentially solved almost all of the scales. And it also, I was interested in how they agreed with the Kamasa results of this interpretation of timescales. So that's how we started. Eventually, it was interesting kind of replicating some results. And then at some point, it became kind of obvious that apparent that it can be solved by hand. And it did. We were able to solve it and turn it into an eigenvalue problem. So this is a linear problem. You can actually add solutions. It depends on a single initial condition, and you can add and recreate many different cases. There's the solutions depend on one single canonical parameter, which is a Q parameter, which contains all of the physics of the problem. It's a product between the Peclet number, which kind of measures the relative strength of diffusion against advection, and the wave number of the initial condition. Essentially, what is the tracer? What does it look like spatially? And because it's a product, then a single value of Q can result from different combinations of values of those. So that was very interesting. The decay, so the solutions are actually as an infinite sum of these modes, each of them multiplied by an exponential decay in time, and the decay rate is given by the frequency, which is proportional to the eigenvalue. So all of the information is contained within this single canonical parameter, which was very interesting. One of the things that actually arose from the simulation is that the eigenvalue system is non-Hermitian, meaning that not all the eigenvalues are real and different. They are all, but so it's not guaranteed, but they are real and different when the values of Q are much more less than 1. In fact, it's less than 1.468. For values before that or smaller than that, all of the eigenvalues are real and different, and therefore solutions decay diffusively, a pure diffusion process. But if you start to increase values of Q beyond that value, you start seeing modes that become complex conjugated in their eigenvalue, which means that they counterpropagate. So that was a very interesting result that we found initially. And essentially means that you can construct solutions that behave like waves, but in the sum they describe how the tracer gets advected and diffused by the shear, by the effect of the jet. Within those frequencies, within the eigenvalue, we can sort of estimate how the location of the Peclet number depends on the location of the exceptional point depends on the Peclet number. So for example, again, a single value of Q can result from different combinations of value of the wave number of the initial condition and the Peclet number, and the exceptional points which mark this transition from diffusive to propagating solutions. Those exceptional points happen at fixed values in Q, meaning that if you increase Peclet number, you can displace the location of the transition regime moving into the left of your screen, so towards smaller values and the wave number. So as you increase the Peclet number, which means the advection dominates, then all of your solutions will behave this propagating, will have this propagating regime, which was very interesting. So with this, then we were able to get animations of solutions. I hope you're seeing them. Essentially, an initial condition that initially has no dependence in Y, but it behaves like a Gaussian in X. So you can recreate solutions like that, construct them. You can change the width. You can change what the cross-jet structure looks like too, which was very interesting. In this case, the Peclet number is 2000. So in fact, all of the eigenvalues propagate in this regime. None of them decay as a pure diffusive process. You can also come up with change the Peclet number, which essentially the flow behaves more diffusively. And in this case, you have some solutions that do not propagate, so they just decay. But it takes a while, it takes a long time in order to hit the pure diffusion regime. So initially, once you run the solution, you forward it in time the solution, everything that dominates is the advective part, the propagating part. But you can actually be more creative and look at more complicated initial conditions like a Gaussian, localized, center image along channels. And then you can play of how the Peclet number affects it. So that was really, really nice, we thought, really interesting. And then essentially we were able to confirm the results from Kamasa, essentially that for certain values of the wave number that is way bigger than a threshold, you have solutions that propagate. So this is an anomalous regime, essentially a vective transport. The tracer doesn't decay, it just gets moved really fast along downstream, which is the rapid stage that Peter Rines and Emil Young talked about. But because we have the whole space of the solution, we can actually pinpoint the scale at which this transition happens for a given value of the Peclet number, and also a given time scale at which all of the propagating modes decay and die. And all of that's left is the diffusive, pure diffusive regime. And these timescales are is exactly at 1.91 units of diffusive timescale. After that, from the initial condition, all of your solutions behave like an effective diffusion regime. Before then, you have a lot of propagation. You have this anomalous regime, which was, again, it agreed a lot with what Kamasa was talking about in this local analysis that were just in the region where the velocity field had an inflection point. And then inspired by Alimani in their work, we thought that the simplest thing to do, which is to look at what the closures were, given that we have the solution for the whole regime, any value of Peclet number and initial conditions. But at the same time, we can also come up and be more creative what the averaging filters were. So for example, in this case, in the left figure, you see initial condition that is independent in Y. So like a dye tracer doesn't vary in the cross jet direction, but in the figure on the right, they have essentially kind of like similar initial conditions, but the solution is localized at Y equals pi over 2, just a double, like a radial Gaussian. So you see that it's only, you see a propagation to the left. So any closure will actually have to figure out how to include all of these behaviors in a way that it makes sense. And we were kind of lucky that we were able to come up with this simple result, and the closure actually proportional to the eigenvalue. So all of our insights from the eigenvalues themselves and how they depend on Peclet number, you can look at how they become operators in physical space. So for example, again, at long time scales, scales that are much smaller than 1.468 divided by the Peclet number, everything is purely diffusive, and you can recover a closure for the massive function, for the eigenfunction, that is a kind of like an effective diffusion regime. And the parameter, the effective diffusivity, matches exactly what the theory should, from back in the 50s, what they said it should be. The other regime, which was the interesting anomalous regime, you also look at those, you can also figure out what the closure for that regime is. And essentially you recover a fractional order operator, which is a combination of a pure linear advection by the amplitude of the jet. In this case, the cosine has a maximum plus minus 1. So essentially you have this kind of like, that's where the cone is in this mean. And then you have a fractional order operator, which essentially dictates that the tracer decays really slowly. If you were to apply like an diffusion, effective diffusion everywhere equally, you essentially will impose that the tracer decays really sharply, as opposed to having long-lived anomalous fluxes out of the subgrid boxes. So with this kind of stuff, we thought about that given a general averaging filter, we have this kind of like 2 timescale closure that they incorporate the scale dependency, given this phenomena that we saw, and therefore we were able to kind of like propose a closure that it's dependent, it's just a timescale separation behavior. And within it, given the averaging filter and how you project an initial condition on the Matthew functions or the eigenfunctions, you can recreate this type of localized initial conditions that have a Y structure, which we consider is very promising. And just to finish up, I think the summary and one of the things that we were excited about the cosine jet is that it's really the simplest case. The cosine jet is the simplest case in which the jet has a Fourier structure. So you can come up with something more complicated. And in fact, we've been able to expand our analysis, which is, again, there's no data, it's just mathematical solutions, into cases in which the velocity field is localized like a Gaussian, just a jet, but it's just localized rather than having a irrealistic cosine structure. And again, we were able to construct solutions and kind of like recover some of the asymptotics that we were from the previous literature, and provide something that might be potentially useful for transport modeling, aside from what the really cool stuff that Manny and Park had done. And then I just want to end with this idea that, again, we can expand upon this method, and we've kind of been able to do this kind of stuff for several cases of jet flows, and which is very exciting. And one of the things that we're interested in applying in terms of oceans, tracer dispersion, and is that effective shear dispersion induced by gravity waves, vertically propagating gravity waves onto the passive tracer field, which I think needs to be revisited given our analytical solutions. And with that, I say thank you, guys, and I hope I didn't bore you with all of this mathematics.
Miguel, thanks very much for a very stimulating talk about this complex problem. Let's see, if you stop sharing, I will ask Laure to share her slides while I introduce her to the audience. So Laure Zanna is professor in mathematics and atmosphere ocean science at the Courant Institute of Mathematics and the Center for Data Science at New York University. She received her PhD in climate dynamics from Harvard and was a faculty member at Oxford before moving to NYU. She was the recipient of the 2020 Nicholas P. Fofonoff Award from the American Meteorological Society for exceptional creativity in the development and application of new concepts in ocean and climate dynamics. Her research focuses on the influence of the ocean on the climate at both local and global scales. Her recent work includes understanding the role of the ocean dynamics in ocean heat and carbon storage and sea level under climate change, and developing physics-aware machine learning models. Recently, she received a major grant from Schmidt Futures to lead an international research team to use cutting-edge machine learning methods to improve climate models and to incorporate many complex processes, including ocean ice, atmosphere, and so on. So so now I would like to pass it on to Laure and let you start your presentation.
Great, thank you very much. Hopefully you can see my screen. Thanks everybody for joining, and it's great to actually come just after Miguel, who already introduced you, to the problem and the complexity of the climate system and finding what we call parameterization, which is, trying to actually capture the, many processes that are not resolved in climate models. And this is what I'm going to show you here today, but rather than, starting with some kind of beautiful theory, I'm going to start from data. And this is really kind of the way we're going at it, which is how can we blend physics and data and machine learning to actually try to represent many processes that we can't resolve in the climate system. And so hopefully I'll show you that there's a lot of work to be done. And Miguel already showed you that, there's a lot of theory that goes into it, and yet many aspects remains, to be understood. And so the question is, can we use data and physics and theory together to actually make, a step forward that can be transformative to some extent. So as always, I'm the one speaking, but a lot of the work is done, by amazing people, former PhD students from Bolton who now work for GitHub, and a current postdoc, Arthur Guillaumin, was at NYU and starting a faculty job in September in stats and data science. Okay, so we're going to take a little bit of a step back and kind of, remember what the ocean is, or what do we know about the ocean. So the ocean is basically covering 70% of the surface of the planet. It's a massive heat reservoir, and here I'm showing ocean heat content, which is basically how much warming we've been seeing over the past 150 years. And so what you see is that things are getting redder or yellower, meaning that the ocean has been taking up more heat, more energy that we've been putting into the climate system is being absorbed by the ocean. So about 90%, more than 90% of the excess energy that is due to anthropogenic climate change actually ends up in the ocean. So understanding how tracers, as Miguel has been talking about, how temperature and carbon are taken up by the ocean is actually pretty critical. And a big component of that is how this heat and carbon are being moved around, how they're being steered, and how they're being mixed. And so how do we know that the oceans are going to continue to warm? Well, the more we emit, the more we're going to continue to take up. But the rate at which we take up heat and carbon is definitely affected by, again, many processes that we do not resolve in climate simulations. So again, Miguel kind of pointed out the fact that, we use climate models, and they're amazing. I'm a big fan of them. I've been using them for a very long time. And here is a simulation. So it's the same climate model, but solved on basically same grid, but a grid that has a different horizontal resolution. So we're still looking at ocean temperatures here in this kind of climate simulation, And the one on the right has an horizontal resolution that is about 1/10 of a degree. So basically a box that is 10 kilometer by 10 kilometer. And as you move towards the left on the screen, here, the horizontal grid is about 25 kilometer by 25 kilometers. So it's getting coarser, right? And you can see things are a little bit more viscous. The flow is not as nice and turbulent and pretty as we see here, because we resolve a lot of important processes. And then if you go again a little bit more towards the left, that's actually kind of a typical resolution of a climate model. 1 degree by 1 degrey, so 100 kilometer by 100 kilometer grid box. So you can, barely see things moving anymore to some extent. So as you increase resolution, you actually can represent more physics. You can represent a lot of those steering and mixing processes that are actually critical for the large scale flow. But unfortunately, your computational cost goes up pretty drastically, and we can't afford to routinely run climate simulations for hundreds of years or for ensembles, which is kind of important for us. So usually we compromise. So we run those equations, but on a coarser resolution grid box. And so of course, the problem is, how do you represent the physics that is missing at those kind of coarser resolution models without having the computational cost of running at high res? And that's where, the closure problem comes about that Miguel talked about. And for, decades, climate models have been doing, what we know we can do is, okay, can we represent all the processes that are not resolved on that grid? Clouds, for example, in the atmosphere, right? So they're going to have scale that are much smaller than this kind of 100 kilometer by 100 kilometer grid boxes that we're talking about. Same for ocean turbulence and mixing and steering that Miguel was talking about. So here we're looking at kind of a satellite image of again, turbulence in the ocean. So what we've been doing, again, for the longest time is say, okay, well, let's try to actually, represent what those clouds or any processes that is happening below the grid box size will do on the large scale, right? So then all you need to know is some kind of property of the resolved flow. And so in the ocean, you can think about, oh, well, all I need to do is something about the gradients of the tracer or the gradient of the velocity. And I'm going to write a mathematical operator that will actually mimic what mixing and turbulence are supposed to do. It works great. But nonetheless, our models are still biased, meaning that they don't reproduce accurately many properties of the climate system that we care about. And that means when we use them for projections, they will have, embedded errors in them. And, and it's okay. We've kind of, it's still a pretty good representation of the climate system, but can we make those simulations more accurate? So rather than start by saying, well, I know roughly what those processes are going to do on the large scale, can we actually let the data speak for itself? And that's really what we're going after. So rather than starting by a mathematical operator that will know, will do something to the flow, we're going to say, okay, let's take all the data that we have. And so, we have more data than we ever had before that we can't even process for the most part. We do have high resolution simulations. We just don't have a lot of them, but we still have plenty. We have new observations that are coming and more coming along the way. Can we use this wealth of data with the power of machine learning, which can extract information from that data set to tell us what will be the effect of, say, turbulence on the large scale flow? So then we can go and plug it back into a climate model without making the assumption that we already know what the mathematical operator will look for. That's what my group has been doing for the last several years. I'm not going to show you the most up-to-date result because we're doing a lot of stuff, and I'm happy to take questions and comments at the end. But I'll show you how we actually try to not have this world of, oh, only data and machine learning versus only physics. We really try to bring the two of them together to actually make the best out of our understanding or the way we constrain the physics and what the data is teaching us. So I'm going to show you one example first, which is we're going to take some idealized simulations of the ocean, so fairly turbulent, and we're going to learn what is the missing forcing. So basically, what is the missing term that we would need to represent in a coarse resolution simulation. So we're going to take a lot of data from those high resolution simulations, and the input is going to be coarse resolution velocities. Then we're going to ask a neural network, in this case, convolutional neural network, so can extract something from 2D images. to actually, again, optimize for this missing force. So what is the missing closure that I would need to have in a coarse resolution model to represent the turbulence as a function of the resolved velocity? So now what we did in the architecture of that neural network is, because the neural network sees images, it doesn't know physics. If you're lucky, it picks out the physics, but if you're unlucky, it just picks out any features that you want. But we know that we still need to conserve some properties. And so in our case, we're focusing on momentum, and that means I need to conserve momentum, because I can't just have a net input of momentum or a net sink of momentum when I'm going to plug that into a climate model, because it's just going to drift away forever. So within the architecture, we actually embed conservation principles, and you can do that. So you're basically telling the algorithm, okay, you can't learn physics by yourself, but I'm going to impose some constraints. So that's one way to actually blend, physics and data science together. And so we train the algorithm to learn this kind of missing forcing, so this missing parameterization of ocean turbulence that is missing from a coarse resolution simulation as a function of the results in those very idealized simulations. So this is what we're asking, the parameterization to learn. So again, this is the kind of model that we use. If you're an oceanographer, you recognize it directly. It's kind of a double gyre. So we have wind blowing at the surface of the ocean, creates kind of, basically strong circulation on each side here. But the important bit is that you get a very strong jet in the middle. You can think about the Gulf Stream or the Shear, if you're familiar. And that generates a lot of turbulence around it. And that turbulence actually feeds the jet. So it feeds the momentum, feeds the ocean currents, and that's really hard to actually capture. And so we're asking the neural net to actually learn this kind of missing turbulence that is kind of represented here. So this is X and Y. So you can think about longitude and latitude here. That's the standard deviation of that forcing that we're missing. You can see it's concentrated in a jet. So it's very non-uniform, right? So it's a pretty tricky pattern to get, and that's just on the mean, right? So like picking that at every, at every snapshot, every grid box is a pretty tall order. And yet they do amazing. So we basically keep, 50% of the data to train, and then we test it on, the other leftover, if you want. And so that's the mean that the neural net is predicting, and that's the standard deviation, and that's the correlation between the true forcing and what the neural net has been predicting with this kind of embedded physics. So you can see correlation is almost one everywhere, right? So just based on data, it's actually able to capture a model of the missing turbulence. So I find it pretty impressive personally. Of course, you can see regions where it does poorly, but that's actually regions where there's no turbulence. So if you go back here, right, it's all zero. So, doesn't do a good job, but there's nothing to capture. So it's not the end of the world. How does that compare to, say, parameterization that would be based on physics for this kind of momentum closure? And this is what I'm showing here. Just again, the correlation. So you can see the correlation for a traditional physics closure, where you would not necessarily learn from data, but like something that you can come up with. It's actually doing a pretty bad job. It's actually anti-correlated half the time. So the neural net, with its magic, to some extent, does a pretty good job. And that's something that teaches us that there is something in the data that just going at it with just basic assumption is not enough. That we still are missing a lot of important physics that we might be able to learn directly with machine learning algorithms. Now, the downside of it is I have no idea what the neural net is doing here. I mean, it just picked out a great correlation, but I don't know why. And, as a physicist, kind of, baffles me a little bit. So what we're trying to do is say, still, let's question the data, but rather than, asking kind of a black box to learn something, let's try to learn an equation for it. So machine learning has, there are many tools out there. And so one of them is, using what we call sparse regressions. And so that's one of the methods where we're still going to do the same thing. We're going to diagnose the missing forcing, and we're going to ask the algorithm to learn that missing forcing, but we're going to ask it to learn as, the sum of some weight, which is what we're looking for, multiplying by many basis functions. And those basis functions are taken from the data, and they are equations. And so we give the algorithm, velocities, gradients of velocities, gradients of temperature, and so on and so forth. And the algorithm goes and prune through that library of function and select a certain number of functions that best represent this missing forcing. So now we're still using the data. We're not making an assumption about what the equation should be. We're letting the algorithm tell us what that equation should be. we still embedded a couple of constraints within the basis function we give it. We made them so that they can be written as the divergence of a flux. So again, just so you understand is that, so then we can actually conserve properties. And so again, you can still embed additional constraint within what you do. Now, of course, you need to make a selection a little bit, how many of those basis function you want to keep and things like this. We kept a few that represent about 60% of the variance, which is, we could have kept a bit more, but it was simple enough and give us, some kind of beautiful equation that can be written as the divergence of a flux that is symmetric. So again, you don't need to understand any of that, but it has kind of embedded properties of what we know the turbulence should look like. And we were able to actually go and explain what those terms are, what they do to the physics, and the way they actually strain and steer momentum. Now, if we look at the correlation, you can see that it doesn't do as good as a neural net, but still, has a pretty uniform correlation pretty much everywhere, meaning that kind of, discovering equations can be a pretty good, way forward in terms of using the data directly to actually learn new physics. Now, of course, can we get there with just the equation discovery? So that's something we're thinking about as we're moving forward. So now all of that is offline. And so I showed you that from data, we can learn things. We can interpret them in some instances. Sometimes we don't, but we're working on it. But that's not the final game. At the end of the day, we need to take what we learn and plug it in the coarse resolution model and show that it improves the simulation. And that's a very hard test because it's a two-step, basically. So now if we implement that in a model, it's going to be a very idealized model again. It's going to still have this feature of a jet in the middle and kind of different circulation. That's what the high resolution simulation looks like. Again, it's, has a jet in the middle and other circulation, but let's focus on that. That's the standard deviation of the velocity field. And so again, where you have the jet, it's very turbulent. So there's a lot of, variability there. That's the same equation, but on a coarse grid. So same as before, right? It's kind of less turbulent. So you can see there's less standard deviation in the flow. So it's a bit more boring. So now let's plug in our learned parameterization that we learned offline. Plug that into this kind of coarse resolution model and propagate the model forward in time and run it for several years. So that's what we get. If we plug in the equation discovery, and if we plugged in the neural network. In both instances, it's just, again, focused on the standard deviation. They both do a pretty good job overall. We had some numerical stability issues, and I can talk about it forever, but I'm happy to take that during questions if there are any. But overall, learning from data can actually both, discover new physics, new parameterization, and they can have the potential of actually improving climate simulation. So all of that is, of course, proof of concept, right? We're a long way away to understanding all the different closures and what they will do in the climate, in the climate model. And, as mentioned at the beginning in the intro, we're very lucky to have support from Schmidt Future to actually really kind of go and explore those ideas, starting from data and blending physics and machine learning to try to learn new closures and trying to, have better understanding of different climate processes in the atmosphere, like clouds and convection, in the sea ice. So at the interaction between sea ice, ocean, and atmosphere, and in the ocean as well, and at the interface between those different components. So then we can actually plug those new closures based on data and machine learning and implement them in community climate models that are already existing and hopefully improve our climate predictions as we move forward. And it's a big project with many, many collaborators, and it's pretty exciting because we really try to leverage the huge amount of data that we're getting out there to really trying to actually understand better climate processes and hopefully, improve climate models along the way. So I'll leave it at that. And thanks again for joining and for having us. And it was a pleasure to also go after Miguel, where I learned a lot from.
Thanks so much, Laure, for the wonderful talk. And it was so interesting because when we selected the speakers, we asked each of the universities to recommend speakers in very broad themes, but it so happens that the talks that you gave today are such complementary approaches, which is excellent. And I want to thank all the audience members. I know at some places like Michigan and NYU, it's already summertime, and maybe some people's mindset are a little bit leisurely. So thank you so much for joining us today. Let's start with questions from the audience. And just a reminder, you can put the questions in the Q&A. First questions from George Manucharian. Is there, I think this is for Miguel, is there any non-locality in time for the eddy diffusivity closure, i.e. does the effective eddy diffusive depend only on the present state of the mean flow or also on the past?
Is that for me or is that for?
I think so. I think it's for you.
Okay. Yeah, that's a really good question. I know that there are people who have looked at non-locality in time. I haven't. One of the things that that we've done is just to look at steady velocity fields and look at time evolution of a tracer given a steady velocity field. In that case, you have a non-locality in space. But I know people, particularly here in Johns Hopkins, that I've looked at non-locality in time, and they usually get something like a Caputo derivative, which is kind of like a fraction order derivative in time as well. So that is very interesting. When we came into this program, we were not really expecting anything like that. We just happened to have a fractional order operator in space. I know there's probably a relationship between the two of them, but we haven't explored that. So far in the steady kinematic flows that we've considered, it looks like non-locality in space is what we're getting for all the flow cases we're considering. Yeah.
Next question is for Laure from Kyle Kramer. Hi, Kyle. Nice to see you in the audience. So Laura, I think you can see the question too, right?
Yeah, I can see it. Yeah, so I can really quickly. Hopefully, the audience can see it as well. So
maybe,
yes.
Yeah, I'm not sure if the audience members all can see the question.
Okay.
Just
so I'll mention it.
Yeah.
I'll basically mention it. So Kyle is discussing, and I'll share my slide again just to, at least I think that's what we're doing. So about the correlation seen between the equation discovery and the neural net. So the neural net basically has very strong, correlation in parts of the domain, while the equation discovery, the correlation is a little lower, but yet is actually covering a larger extent of the basin. And so the question from Kyle is, is it better, to have a decent correlation over more domain, or to have a higher correlation on a smaller part of the domain? So I would say it's pretty important to have the largest possible correlation in the region where the forcing is the strongest. So where, the turbulence is largest. And so we can see basically is those kind of, those regions over here, which the equation discovery gets there, but not as well as the neural net. So we're still missing something. And so I think, in this case, there is a bit of a trade-off that we're missing in the turbulent region by that. But of course, when we go and implement that in the climate model, then all bets are off. And that's something we definitely are testing. That's definitely a great question. It's very problem dependent as well.
Yeah. I think the next one is also for you, Laure, from Pedram Hassanzadeh.
Okay, I'm wondering if it would be useful to use the equation discovery and neural net-based approach together, given that one is interpretable, the other one is more accurate. Excellent question. So right now, this is kind of our newest little result, is that actually within the loss function, we already basically give the neural net the equation, and we ask it to learn the parameter plus a residual from it. So we feel that it might be the best approach. The more we know, the more we don't need the neural net to actually learn. We can just learn the parameters. And then from that, we let it pick out the residual, and then of course, go and try to interpret that part. So yes, we're actually trying to do that together right now. But it's a tough problem. We definitely are struggling a little bit depending on the data sets that we use. But it's fun, I must admit. Okay.
Yeah, so let's go down the list. I think there's some questions. Next one from Karen Jakar.
Sure. How do you calculate uncertainty of the discovered term using LVM? Yeah, so the equation discovery, which is relevant back to machine. So in this case, so it's sparse Bayesian regression. So the weights are assumed to be Gaussian. And so they have an uncertainty associated with it because we already defined a Gaussian prior in the data. The uncertainty is actually pretty narrow there, to be honest. It's probably, the fact that, the algorithm is pretty good at kind of selecting the basis function. For the neural net, in this case, we have no uncertainty, but we have a new paper that is coming out where rather than learning just the mean in the loss function, we learn the mean and the standard deviation. So that gives us an uncertainty in the missing forcing. So it's kind of another way to kind of do it with a neural net. I never know if I actually really answer the right question because there's no feedback, but I hope, I hope the attendees will tell me if I did not answer the question. Okay, I think the other one is also for me, Georgi. So for the coupled dynamical plus ML system, how to prevent it from drifting into non-realistic phase space region, i.e. regions that are not accessible for the initial high-res system? That's a great question. I think that's the problem of coupling a dynamical model and plus something, whether it's machine learning. I think people had a lot of issue with plugging in machine learning, saying that we're plugging in black box, and shame on us that we're going to break the physics and then the model will drift. And that's true, it is possible. But I think if we manage to do that in, again, having something that first conserve properties, like we did, right? You conserve momentum and you conserve tracer and so on. So that's already the first step. So then that means you keep your conservation laws right. Now for numerical instability, that's usually built into the model itself. So you still need to satisfy CFL criteria and things like this. And so you need to have a good knowledge of the climate model or whatever model you're going to use. So that's why it requires both machine learning experts and dynamicists to work together, because I don't think it's one or the other here. It's really a combination of expertise. I think there's one more. When you say that we now have a lot of data, you're talking about data, which I assume it's observation or model output. Do we have enough oceanographic data to train neural nets? And could you comment a bit on the limitation or something like transfer learning? Yeah, excellent question. So I think for certain processes, we have a lot of data. I think, to learn a subgrid parameterization, no, definitely no. And so that's why we are actually right now using transfer learning. So we are training on model data and now trying to refine with direct observations. And so that's definitely, I think there's a lot of potential there. Now, if that was just to make, direct prediction, so for some aspect of the climate system, with some colleagues at NYU, Andrew Wilson, we've been actually trying to, train neural net just to make sea level predictions. And actually, there's not enough in the data itself, but with transfer learning, we actually do a pretty good job. So I think, again, it will be problem dependent. For the atmosphere, there is more data. Again, for the parameterization, I don't know if that's enough, but you can use it for transfer learning for sure. I think that's definitely an important way forward.
Great. So audience members, if you have questions, keep putting them in the Q&A. Meanwhile, let me ask you maybe a couple of more sort of philosophical questions. I'm not a oceanographer or any climate researcher. I'm actually a brain scientist. So when we talk about sort of the multi-scale integration from the local level all the way to the global level, the same question actually appears everywhere. For example, in the brain, right? You talk about within cellular, cellular activities. You talk about the electrical activity of each single cell, and then the activities of the network and the brain regions. You talk about social networks, then there are individual person's behavior all the way to group behavior, and then to a society's behavior. So this the so-called multi-scale integration is really a buzzword today. The specific mechanisms are different. The math involved are different. but conceptually, what are some of the things that you find are interesting, and what are some of the conversations that you guys have been having with researchers from other domains?
Oh yeah, I mean, as you said, I think multi-scale interaction is definitely everywhere. Doesn't really matter which field you're in, and for us, it's definitely critical, right? So if I want to make a prediction of of large scale temperature, I need to know the tiny scale features, and this is a conversation we have across all different domains. Is how do you represent that interaction the best possible way? Is it random? Or can you use a bunch of random variables, which could be an aspect, well, it can work, right? Or is there more, decision making through that process? And that's definitely that's a wonderful conversation, across field. And as you say, in neuroscience, this happens all the time, right? Basically fire a neuron, but then you make a decision that has a large scale impact to some extent. And so definitely a very common things. That will remain definitely in our mind, since it's the driver, right?
Yeah, and I think for me personally, I feel like I've been having these type of conversations for a long time with some of my friends in mathematics about multiscale modeling, there's this assumption of separation of scales that we've kind of used and reused to get insight into phenomena, which is very important. But I think now we need to start looking into this regime in which you cannot assume that. And that's where you discover all of these really rich behaviors that I think are going to be very interesting to see how we can gain insight into the physics of it and also into the modeling and prediction of it. And it's a hard problem. That's the reason why people assume certain things before. And that's one of the things that I find most stimulating about other fields, of how they try to tackle these things. Separation of scales, also nonlinearity. Those two are just, so those are the hardest questions.
There's another question in chat for Laura again. So,
okay, was equation discovered model stable as in a posterior testing, or did you have to tweak it in some way to make it stable? Both machine learning models, when implemented, were problematic. The neural net was stable, but give us a crazy physical behavior. Kind of, for those of you who are oceanographer, it gives basically kind of forget about the wind force and give me a gigantic eddy for the size of the domain. So it was like kind of crazy, but never blew up nonetheless, which was, I'm still baffled by this. The equation discovery was actually unstable, and we know why. It's just because there were some issues with CFL criteria, and I think we know now how to fix that. So we had to tune down both parameterization to actually get the results we got. And that's always a problem.
Another question just came in for Laura as well.
Okay, so are you able to include any additional constraint, for example, conservation of mass and momentum in the cost function of the neural net? So in this case, we didn't. We did it within the architecture itself. So we literally embedded a last layer where we're taking derivative of a tensor. And so that helped us conserve momentum. You can definitely put it in the loss function. It would be a soft constraint because again, the loss, right? You only tend towards that minimization, and doesn't necessarily enforce it, and like building any of the architecture. But there are several papers out there that do it within the loss. We embed it as well for other problems, but in this case, it was directly in the architecture.
So perfect. Looks like we're right on time. We're 1 minute past. So thank you again for the wonderful talk, for all the participation from the audience members. What we're hoping for is in the next school year, we'll think about ways to engage researchers across these 7 data science institutes, think about ways to collaborate, and hopefully some great ideas will come up. If the audience members or the speakers have thoughts on how we could effectively do this, just drop me an email. So again, thank you very much. We'll hopefully see you in the future in various occasions.
Thank you very much for having us.
Thank you.
Thanks, everyone.